All right, welcome to this explainer on EPA Method 202. I am so excited to guide you through this today because we are going to do something really cool. We're following the methodological journey of a stack emission sample, literally from the exact moment it leaves an industrial stack all the way to its final mathematical calculation in the lab. Now, measuring condensable particulate matter, it's incredibly complex, but by breaking it down step by step, we're going to make this highly technical procedure totally approachable.
Because this is a strictly regulated procedure, here's our roadmap for today. First, what is Method 202? Second, assembling the sampling train. Third, collection and field purging. Fourth, train recovery procedures. Fifth, the analytical lab procedures. And finally, final calculations and reporting.
Let's kick things off with Section 1. What exactly is Method 202?
So our absolute target here is condensable particulate matter, or CPM. Think about it like this. When emissions are inside a super hot stack, certain materials are just in a vapor phase. They completely bypass the standard heated filters we use to catch solid particles. But the second those gases hit the cooler ambient air outside, boom, they condense into liquid or solid particulate matter. And by regulatory definition, all of this condensable PM is assumed to be in the PM 2.5 size fraction, which means it's small enough to be inhaled right into your lungs. This specific method is designed to measure these elusive emissions after the standard filterable stuff has already been taken out.
Moving right along to Section 2, assembling the sampling train. Take a look at the schematic. This is our full sampling train, and you'll see it's equipped with a condenser and impingers, which are basically just specialized glass vessels. Notice how they are sitting in water baths? The whole goal here is to artificially cool that stack gas down to 30 degrees Celsius, so about 85 degrees Fahrenheit, or even cooler. By dropping the temperature that drastically, we literally force those vapors to condense right there in our glassware instead of escaping out into the atmosphere.
Now, to get this right, you must connect these key components in an exact, specific sequence. First up, the gas travels through a fluoropolymer-lined or glass probe extension. From there, it hits a Method 23 type condenser, which is immediately followed by a water dropout impinger and then a modified Greenberg-Smith backup impinger. Once it's through those impingers, the gas moves through a specialized CPM filter holder, and finally, it hits the moisture traps packed with silica gel. And here is a massive, absolutely crucial takeaway for anyone working in the field. You add 0 water to those first impingers before you start sampling. None. You want to collect only the condensed moisture coming directly from the stack itself.
All right, Section 3, collection and field purging.
So you've pulled your sample. Great. But you cannot just pack up your gear and go home. You have to immediately run a post-test nitrogen purge. First, you detach the probe. Second, you make sure the impinger tip is submerged at least 1 centimeter below the liquid level. If it's not, you have to add ultra-pure degassed water until it is. Finally, you push ultra-pure nitrogen gas through the entire system at a rate of at least 14 liters per minute, and you do that for 1 full hour. This nitrogen purge is absolutely mandatory because it removes dissolved sulfur dioxide gases. If you skip this step, that sulfur dioxide will react with oxygen to create false particulate matter, or artifacts, completely ruining the accuracy of your sample.
Real quick, before we pack up these highly sensitive samples and head back to the analytical lab, make sure to subscribe to the Explainer series so you never miss a deep dive like this. And hey, if you're out in the field or the lab and you need some direct support, or you just want to talk shop about these methods, shoot an email to qstpprepacademy@gmail.com. We absolutely love hearing from you guys.
Okay, Section 4, train recovery procedures. To build a truly accurate profile of those emissions, you have to rigorously separate your train catches into very specific leak-proof containers. Container 1 gets the aqueous, or water-based, liquid from your impingers. Container 2 is a big one. This is for your organic rinses. You meticulously rinse all your glassware twice with acetone and then twice with hexane, just to capture every single bit of organic material clinging to the glass. Container 3 is where you safely store the CPM filter. And finally, containers 4 and 5 hold the remaining cold impinger water and the silica gel, which you'll weigh later to figure out the total moisture content of the stacked gas.
Let's move indoors for Section 5, the analytical lab procedures.
This breaks down some highly dense analytical work. Essentially, you are separating the organic and inorganic fractions so you can weigh them accurately. For that filter in container 3, you actually sonicate it. You hit it with sound waves in a water bath and then a hexane bath to extract the material. As for the aqueous liquid in container 1, You put that in a separatory funnel with hexane to pull out any lingering organics, and then combine those organics with container 2. Finally, both the aqueous and organic fractions are painstakingly evaporated down, desiccated for 24 hours to suck out any last bit of moisture, and then weighed repeatedly. You keep weighing them until you hit a constant weight, which just means the scale doesn't change by more than half a milligram between weighings. It is intense, exacting work.
And that brings us to our final stop, Section 6, Final Calculations and Reporting. By adding your dried inorganic mass and the organic mass together, you finally get your total CPM mass. Then you plug it right into this exact formula, equation 5, to calculate the final concentration. You're just dividing that total condensable particulate mass by the volume of the gas sample you pulled through your meter, corrected to standard conditions. Conceptually, it's pretty straightforward, but operationally, as you've seen, it requires incredible discipline to get right.
Now, here's a number that will blow your mind. When the EPA ran field evaluations for this revised method, they found a precision of approximately 4 milligrams for total CPM. That's about 0.5 milligrams for organic and 3.5 milligrams for inorganic. To really put that into perspective, 4 milligrams is roughly the weight of a single grain of sand. Think about that. That proves just how insanely sensitive these procedures are. It's exactly why perfectly cleaned glassware, ultra-pure reagents, and flawless nitrogen purging aren't just recommendations. They are absolute non-negotiables.
Precise stack testing plays such a critical role in protecting our environment. Condensable particulate matter is a massive contributor to the PM 2.5 pollution affecting health all over the world. So as industries keep evolving, knowing how to master complex measurements like this is exactly what's going to define the future of our air quality. Keep investigating these standards, respect the rigorous science behind them, and always remember why this accuracy matters for the air we all breathe. Thanks for joining me today, and I'll catch you on the next Explainer.